All right, let's just jump right in. We're going to explore something you walk on every single day, but probably never really think about. We're going underground, into this hidden, super complex, and honestly, absolutely vital world that's right there, just under our feet.
And, this isn't some new mystery. Get this. Over 500 years ago, Leonardo da Vinci himself said that we know more about how the planets and stars move than we do about the soil under our own feet. And what's crazy is that's still kind of true today. It's why soil is one of the last great frontiers for scientists.
So, when you look at a clump of dirt like this one, what do you see? I mean, it looks pretty simple, right? Solid, basic. But what if I told you that inside there's a whole universe of tunnels and chambers and hidden pathways? That's what we're going to do. We're going to pull back the curtain on this incredible, complex architecture that's hiding in plain sight.
Okay, so first things first, let's look at the physical stage where all this magic happens. We're talking about the soil's pore network. Just think of it like a massive system of hidden highways.
Now, the biggest of these highways, the interstates, if you will, are called macropores. And these aren't just random holes on the ground. No way! They're super important channels that are literally carved out by things like burrowing earthworms or old, decaying plant roots. They're the main arteries for water, for air, for life itself, really.
And what's so cool is how we can even see this stuff. Scientists are using X-ray CT scans, the same kind of tech they use in hospitals, to literally peer inside a clump of soil. And look at this. You can see how the network on the left is super dense and all interconnected, but the one on the right is way more open, kind of branching out. It just goes to show you every single piece of soil is its own unique labyrinth.
All right, so we've seen the highways. That begs a question, right? How does the traffic, and we're talking mainly about water here, how does it actually move through this crazy maze? Well, the answer is probably not what you think. It kind of turns a common misconception on its head. I mean, if I asked you, you'd probably say, well, water flows down, right? Because of gravity, and it moves from a wet place to a dry place. Simple. That just makes sense, doesn't it?
Well, about that. It turns out our common sense is actually wrong here. In the world of soil, water can flow up. It can flow sideways. It can even, get this, flow from a drier spot to a wetter one. It's not just about gravity. There's another much more powerful, invisible force at play.
And that brings us to the key concept for this whole thing, soil-water potential. The easiest way to think about it is like water pressure. Just like air in a balloon, water will always move from a high-pressure zone to a low-pressure zone. It doesn't care about up or down. This potential is the real boss here. It's what's driving the whole system.
So figuring out this potential thing was a huge leap forward. But it's not enough to just know which way the water's going to go. We also need to know how fast it's going to get there. And for that, we have to thank a French engineer who totally cracked the code.
Let's meet the man of the hour, Henry Darcy. Back in 1856, he was working on a pretty practical problem, designing sand filters to clean drinking water. And in the process, he stumbled upon a groundbreaking discovery that would become like a cornerstone for all of soil physics and hydrology.
And what he gave us was this beautifully simple little formula. It basically says the speed of the water flow depends on just two things. First, something called hydraulic conductivity, which is just a fancy way of saying how easily water can move through the soil. And second, the gradient, which is the strength of that push from the water potential we were just talking about. Suddenly, for the first time ever, we could predict this invisible, super complex process with a simple, elegant equation. It was an absolute game changer.
So let's just break that down one more time. Step 1, you've got the gradient. That's the push. Step 2, you've got the conductivity. That's how wide and open the highway is. You put those two together and voila, you get the flow, the actual movement of water. It's just such a neat way to think about a really, really complex system.
But of course, it's never that simple, is it? Darcy's law was just the starting point. I mean, he figured it out using nice, uniform sand in a perfect lab setting. The real world under our feet? It's way, way messier.
For starters, that whole conductivity thing can be all over the place. It totally depends on the type of soil. Just look at this chart. Water zips through sand over 300 times faster than it creeps through a clay loam. That is a massive difference in how easily that highway lets traffic through.
And here's the real kicker. That 300 times difference? That's when the soil is soaking wet, completely saturated. But most of the time, soil isn't totally full of water. It's what we call unsaturated. So what happens then?
Well, this experiment shows it perfectly.
What they did was flush fresh water through a column of soil, and that caused tiny clay particles to basically fall apart and clog up all the pores. Just look at that insane drop in the graph. The conductivity, the ease of flow, just plummeted by over 90%. The hidden highways just turned into a total traffic jam. Gridlock.
So trying to account for all this real-world messiness, the complex pores, the fact that the water content is always changing, all these chemical reactions happening, that's one of the grand challenges for soil scientists today. They're trying to build new models that can actually handle the messy reality of this dynamic underground world.
So after all this, you might be asking, okay, but why does any of this matter? Pores, potential, conductivity? Who cares? Well, we all should. Because this invisible world pretty much governs our world. It dictates how well our crops grow, it's what filters the water we drink. It's the literal foundation for entire ecosystems. And it even affects super practical stuff, like whether or not you can even install a septic system on a piece of land.
Okay, so let's boil it all down to 3 key things you should remember. First, soil isn't just dirt. It's a huge network of hidden highways. Second, water flow isn't just about gravity. It's driven by this invisible force called potential. And third, Darcy's Law gives us a really handy, simple way to start understanding this incredibly complex flow.
So I'm going to leave you with a final thought. The next time you're walking on the ground, whether it's in a park, a field, or just your own backyard, what are you going to imagine is happening down there? Because it's not just dirt, right? It's this complex, living, dynamic world filled with invisible forces and hidden highways, all performing this constant, silent dance right under your feet.